Hello, today we're going to start a new lesson 14.1 from Algebra 2, Volume 2, page 703. It's about fitting exponential functions to data using the function fx equal ab power x. As a reminder, for the exponential growth or decay function, we must have a common ratio between the terms of fx. We're going to look at some examples to determine if this is a exponential function or a linear function. For the linear function or a linear growth or decay functions, the common difference, there's a common difference like addition or subtraction between the terms of fx. So from there's two tables in page 707. We're going to take these two examples to determine if this is exponential function or linear functions. So from the first table A, we see the x value is 0, 1, and the fx is 1, 4. So if we can try to subtract fx1 from fx0 or to determine if there's addition or ratio or multiplication between the values. So if we do the subtraction, 4 minus 1, which is 3, 16 minus 4, which is 12, so that's not a common difference. So we'll try to do a division. 4 divided by 1 is 4, 16 divided by 4 is 4, 64 divided by 16 is 4, 256 divided by 256 divided by 64 is 4. So we can see this multiplication of 4. So 1 multiply 4 is 4, 4 multiply 4 is 16, 16 multiply 4 is 64, and 64 multiply 4 is 256. So that means this is exponential function. For the second one, if we do the division like we did in the value in the table A, so if we divide 7 divided by 1 is 7, 13 divided by 7 is not 7, is 6 point and fraction, so that's not multiplication relation or ratio, so it's not a ratio. But if we do 7 minus 1 is 6, 13 minus 7 is 6, 19 minus 13 is 6, 25 minus 19 is 6. So we can see there's a growth, and this is a growth as well, a growth ratio, and this one the growth incremental or increase. So so that means it's a linear growth function, and this is exponential growth function. Now in real life, the exponential functions, the ratio for exponential functions, it could be in real life not an exact value. So what we can do is doing an average of the ratio between the terms. So we're going to take an example from for real life to talk about how the ratio can be calculated for exponential function where the ratio is not fixed number between the terms. So we're going to take example 1a in page 705, and it's we have a table given to us. So in the table, let's look at the question first. So the question about the growth, population growth in the United States between the year of 1790 to 1890. And there's a table given to us showing the values for each year for the population in millions. So in 1970 it starts with 3.93 million, goes all the way to 1890, goes to 62 million, 62.98 million. So we need to determine, based on the question, we need to create a approximate exponential model for the data set, and then graph it with a plot of the data to assess this fit. So from the table given to us, we can determine the initial value for the function. So the function, the base function we're going to use is the fx equal ab power x, and from the table we determine the f0, which is the initial value, equal 3.93 in millions, just to reduce doing rounding and reduce the space of the numbers are given in the table. If we take f1, that will help us to determine what rate was used for the f1 population increase in 1800. So based on the table, the 1800 is given to us as 5.31 mil population. So by adding that value for the f1, which is 5.31, equal the initial value, which is 3.93 multiply b power 1, which is b. So we divide both sides with 3.93 to move the value to the other side. That will give us the estimate b value. When you divide 5.31 divided by 3.93, that will give us 1.35. That's the estimate ratio for f1. Now it's given to us 10 values. So from 1790 all the way to 1890. So to determine the average ratio for the table set, the table or the data table was given to us, we can calculate the ratio for f1, f0, f1, then f1, f2, f2, f3, f4, f3, f4, all the way to f10. We can add these ratios together and divide it by the data set we have, which is 10. That will give us an estimate ratio of 1.32. So this way we can determine what's the function we'll be using to graph the table. So by replacing the values in the function fx equal a, which is 3.93, multiply the ratio we came up with, which is 1.32 power x. So I took a sample data to able to draw the graph. We took the f0, then f1, f2. The f0 is going to be a value, which is 3.93. Then f1, f2, which is 5.19. Then f2 is 6.85. We did a quick graph. Now this graph goes to the value of 10, actually, and this is not an should be a dot. So the value is from 0 all the way to 10. So this is the represent decades since 1790. So each one is represent 10 years. So from 1790 to 1800, then 1810, all the way to reach to 10. And the y-axis is the population in million. So we get 10 million, 20, 30, 40 to 80 million. And this is how the graph will look like with the points we have. So that's all for today. If you have any questions, feel free to reach out. Thank you.